This will be the last lecture on machine-level programming. We call it advanced topics, but think of it more as miscellaneous topics. And I think most of you, of course, you know that your bomb labs are due tonight, so most of you are probably well into that, or hopefully through it. And then at midnight tonight, the next lab will come out, which is called Attack Lab. And there was a recitation about that yesterday, but this is a lab that's new to the course. It's similar to one that we used to use at this point in the course, but it's been updated and changed in significant ways. So we're actually, when you have labs like we do in this course with this many students, there's a lot of things that can go wrong. So we're going to keep a close eye on how things are going. But I'd encourage you, you only have a week and a half to do this next lab to get started soon. And partly by having some people start sooner, you'll start breaking things for us that we can track down. So today what we'll talk about is a couple, like I said, it's miscellaneous topics, but important topics. One is just sort of what does the memory look like when you're running x86-64 programs. The other is a very important topic on security vulnerability called buffer overflows. And in fact, Attack Lab will be precisely exploiting those security vulnerabilities. And then we'll look at unions. So far, you've looked at arrays and structs and how they're organized. And I want to compare that to unions. So let's talk about memory then. As I said at the beginning, early in the course, conceptually, a memory is just a big array of bytes. And that's the view of the machine-level programmer, even though it's not the actual implementation. There's a whole part that we'll talk about later in the course of this is called virtual memory, this organization, this very simple organization. But the underlying implementation is this complex management of various different memory types, from disk memories to solid-state disks, and to what's called DRAM, which stands for dynamic RAM. When you buy memory for your processor, it's DRAM. So as you know, in x86-64, we're working with machines that nominally have addresses can be up to 64 bits long. And if you work out the numbers, remember I told you at the beginning of the course, you can estimate how big a number like 2 to the 64 is by remembering that 1024 and 1000 are very close to each other. So 2 to the 10th is roughly the same as 10 to the 3rd. So you take 64 and you think 60. So how big is 2 to the 60? Well, that's 6 times 10. And therefore, it's 6 times 3. It's like 10 to the 18th. And then you add the 4 to that. That's 2 to the 4th is 16. So it's around 16 times 10 to the 18th bytes. So if you were to go off and look online on Amazon for DRAM chips and try to buy that much memory, you'd find you're spending a lot of money. More than you, I don't know the numbers, but it would be a lot of money. And so you basically can't do it nowadays. 10 to the, and so right now the machines limit you to actually only 47 bits worth of address in the address space. And so 2 to the 47th, again, work that out, that's like 10 to the 12th times 256 times 10 to the 12th. So it's 256 terabytes. And as you know, you can buy a disk drive now that has 8 terabytes. So it doesn't seem like that much. But if you tried to buy that much DRAM, again, you'd have to have a pretty big credit card limit. And so even that's a huge number. And modern supercomputer installations actually will have almost that much memory. But the point is that the hardware of today limits you to 47 bits worth of address. But that's not really a real limitation in terms of actual machines. And what will happen is memory prices get cheaper and the technology gets better, they'll slowly start adding as succeeding generations of processors come along, let you have bigger and bigger range of addresses. So all that is to say, that's why this number shows up, which is a 7 followed by 11 Fs. I can tell I need to scribble some numbers. You guys aren't, just saying numbers in the air is not working here. So let's try. This. Okay. So remember, I said before, 2 to the 64 is about equal to 16 times 10 to the 18th. And 2 to the 47th is 128 times 10 to the 12th. So it's 128 terabytes. So what's the number after a terabyte, do you know? 10 to the 15th? How many bytes? Yes? Petabytes, right. And do you know what 10 to the 18th is? Exa. So just as a reference, a company like Google, roughly, it's probably its total storage across the whole enterprise is measured in some small number of exabytes. And it every day is getting several petabytes. I don't know the numbers, they're of course secret, but maybe 10 petabytes or more per day of new data that it's ingesting into its system. So these numbers are pretty huge, but not just totally off the charts. Do you know what 10 to the 21st is? It's called a zettabyte with 2 T's. And it's estimated if you add up all the digital content in the world that gets created, everybody's cell phone camera, every video taken by anyone, anywhere, all year long is a couple of zettabytes a year. So it'll be a while before we're really having to deal with that kind of memory. So just to give you an idea, so 128 terabytes is the address limit on these systems. And so that's why you have to have 7, because you remember that's 1, 2, 3. And then there's F, but there's 11 of them. And this is 111 times 11, so that's 44 ones. And this is 3 ones. And that's where you get 47. And that's the address of the, in Linux, that's where they put the stack, is up at the very top of the address space. And I should tell you, this picture is not at all to scale. It would be impossible to draw this picture to scale. For example, it shows that the stack starts way up at the top. And remember, stacks grow to smaller addresses when you're pushing. And also, we show them upside down, just to make everything confusing. So the stack starts there and it grows towards lower addresses. And on a typical system, it will be limited to 8 megabytes. And you can tell that on a Linux system, at least, with the limit command, which used to be more interesting than it is now, because a lot of things are unlimited. But you see it says the stack size is limited to 8192 kbytes or kilobytes, so it's 8 megabytes. And what that means is if you tried to access any memory via the stack pointer, that was outside of the range of this 8 megabyte range, you'd get a segmentation fault. And then down at the lower addresses, what comes in, what gets put into your program are the parts of the code that come out of the executable file. And so there's a section, and we'll talk more when we talk about linking, actually, about the layout of the memory and the different regions of it. But for some obscure reason, they call where the code is sitting, the executable program, the text segment. I don't know why that's true, but it's the way it is, and that's across many machines. And then the data is, first of all, there'll be a section for the data that's allocated at the program begins. So any global variables that you've declared will be in that section. And then the heap is the part of memory that is allocated via call to malloc, or one of its related functions. And so that varies dynamically. As the program runs, it starts off with a very small allocation, and every time you call malloc, if you're not freeing memory, and so your memory requirements keep growing, it'll keep moving up larger and larger addresses. And then somewhere in the code too, and this can vary by system, is the code that gets brought in that represents the library functions. Things like printf and malloc itself are all library code. They're stored off on disk, and they get brought in, they get linked into your program when it first starts executing by a process known as dynamic linking, which we'll talk about later in the course too, with the linking. And what you'll find in general is that allocations will tend to be either at these very low addresses or these very high addresses as your program is running. So just as an example, here's some code that its only value is to show you where things get located. And so you'll see I allocated a fairly large arrays here. This one is, they're all chars, but this is 2 to the 24th, so it's 16 megabyte array. And this one is 2 to the 31st, so it's 2 gigabytes worth of array. I found that if I tried to allocate larger ones, the program wouldn't run. And I also do here's just a sort of global variable, and here's a function. And then there's a single function here with some local variable, and that will be allocated somewhere on the stack. And then there's several calls to malloc, some of which are for some very small chunks of memory, and some are for some very large chunks of memory. And so we can run this program and see what addresses pop out of it. And what you'll see is the stack, this local variable, is somewhere up with an address in the range of the stack, and you see the 7 and a couple Fs, and then it goes to something else. And you'll see also, interestingly enough, that the code that, and then looking down at the bottom, this yellow color is things get relegated to the text segment, the main function and this function I declared called useless. And then the predefined arrays that were, in other words, globally declared, not declared by malloc, they're declared as part of the program itself, are down here in this data section. And because it's a very large array, the huge array, you actually get some fairly large addresses. And then interestingly enough, or I don't know why it's interesting, but for one reason or another, it happens that the smaller chunks of memory allocations are down here at addresses that are actually just a little bit above the pink section, right? And similarly, the really big chunks of memory I allocated are way up here near the stack limit. And they, and so they're there. And in general, what's happening is if I were to try and reference a memory address in this empty range, I'd get a segmentation fault. It's a valid address in terms of its bit properties, but it hasn't actually been set up and allocated by the virtual memory allocator. So at any given time, the valid addresses are just those in the lower portion or the upper portion of these address ranges. And the middle is sort of no man's land. And then what happens is you keep allocating more with malloc, and it will push the limits of what's addressable in toward it. And in principle, if you ever got too much of a memory request, these two would hit each other, and and malloc would return 0 at that point. But it's highly unlikely, given that you have 128 terabytes of memory address range here. So that just, and you've probably seen this when you're running, you're looking at disassembled code with GDB. You're seeing some addresses that are way up here with the 7 and some Fs. Those are stack addresses. And you see these 4s, a lot of 0s and some 4s. Those tend to be where the code is lying too. Question? Yeah, why doesn't the heap proceed in one direction? I actually don't know. I'll just observe that it had a strategy of putting big things here and small things here, and it probably uses slightly different management strategies for those two. Okay, so but I think you'll find that kind of useful to have some sense when you're running GDB. It helps to just have some idea of what's going on when you're looking at these different addresses. Okay, now let's talk about buffer overflow. And we'll start this, you remember on the very first class, and I think we might have reviewed this partway along, we showed this example of some programs where if you do an out-of-bounds reference and write a value that's out of bounds. In particular, I only have an array of 2 elements here, but this function will take an arbitrary value of I and assign some magic number to element I of the array. And it has the possibility of, and we saw that when you do that, if I gets too big, it will first corrupt the double that's stored as part of the struct. And then when it gets bigger, it seems to not have any effect until it gets too big, and then you start corrupting memory. So the basic point is that it's very easy in a program, a C program in particular, to reference memory that's not part of the sort of intent of the program. This can happen in programs that aren't properly written, and it becomes a security vulnerability if there's some way for an outsider to overflow a buffer. For example, if there was some way for an outsider to give a larger value of I and ask that that value be stored there, it could crash the program. And so in general, when you're writing code, you try to think about, can I trust this value? Is this a value that's been computed by my program and I'm sure that it's within bounds? Or is it something that's come from an external source and there is potentially at risk of being a vulnerability? And so in particular, there's a huge class of errors that have to do with overflowing buffers where they're trying to store a string of some type that's been read from a message, and without knowing in advance how big that string is, it's possible that it will be too big for the buffer that's been allocated. And so one of the culprits is there's a whole class of library functions that let you store something, a string, somewhere without any kind of bounds checking even being possible. So the sort of worst one is one called getS. And the purpose of getS is normally it's used to read a string from an input, from a terminal input, something that somebody's typed into a terminal. And so what it's doing is it's scanning this input string and looking for a character that represents the end of the line, which we write in C as \n, and it has a character code in hex of 0A. And so getS, this is sort of an approximate version of what the code for getS looks like. And it's, as an argument, it's just given a destination of where to store the result. And all it does is it reads one character at a time, looks for an end of file, meaning that the input stream is closed, or an end of line. But as long as, until it sees that, it just keeps adding more things to the end of this buffer. And so typically, when somebody calls getS, they'll pass it a pointer to some buffer that they've allocated. But the function, and it will just, getS will just fill that buffer up, but it can potentially just keep going. There's nothing in the function, there's not even an argument to the function that tells the function when it has to stop, when it's reached the limit of it. So it was written that actually getS is, if you try to compile code with getS, it will flash up a big warning that says, this is really an unsafe function. You probably shouldn't even be using it because it was written in an era in the 1970s when the early Unix distributions were coming out, where people just weren't worried about security vulnerabilities. And they just assumed that if you allocated a big enough buffer that there's no reason why a string should be bigger than what you've allocated. And that's actually true with other functions like strcpy. You recall strcpy has two arguments, a destination and a source. And its purpose is to copy the string at the source into the destination. And the way it determines the end of the string in the source is when it hits a null character. And it just keeps copying one by one until it hits that. But it has no way of knowing. There's no information there about how big is the buffer allocated at the destination. And so it can easily overrun that. A similar one called strcat, which is used to concatenate two strings and copy them to another destination. And the scanf functions also have possible in the format string, you can give the %s directive to the format string, which says read in a string and store it someplace. And it doesn't say how long the string is limited to be, and it doesn't say how much memory is available at the destination. So again, it can easily just write over that buffer. So these are real vulnerabilities, and we'll talk in a minute, a little later, about how you as a programmer can be a little smarter than this. But in their sort of raw form, as presented, they have this vulnerability to them. So let's look at an example of what can happen there. So imagine, for example, we want to implement an echo function. So an echo function is one that you just type something in and it prints it back out. It's a very uninteresting function, except it's very useful to demonstrate things. So the idea is it has this little buffer. It's only enough to hold 4 characters. It calls getS to read a string from the input, and then it calls putS, which simply writes back out to the output. And and so let me just demo this not very interesting function. So I call it here buffdemo-nsp, meaning it has no stack protector. And we'll see in a minute what a stack protector is. But you see, if you type a reasonably strong small string, let's see, I've got to remember. It can handle more than 4. Actually, as written, it can't handle more than 3, right? Because there should be room for the null character, too, on Terminator. So it turns out with this particular one, if I type in a string of 24 characters, it'll be okay. But if I type in a string of 24 characters, it will hit a segmentation fault. So where do those numbers 23 and 24 come in? Well, that's something we can learn by looking at the assembly code. So here's, and we'll go through this code. So first of all, this is the code for echo then. And you see that echo calls getS and it calls putS. And here's the part of the code where you can tell how much memory got allocated for the buffer. And hex 18 is what in decimal? 24, right? And you just saw that the thing actually segfaults with a input string of 24, so we'll see that in a minute. But anyways, you can see here that it's allocating on the stack a region of 24 bytes, and it's copying that into RDI, which is, of course, the argument for getS. So getS is being called with a pointer to a buffer of size 24, of maximum 24, even though you saw the original declaration was just for 4. And then it calls getS, and then getS does its thing. And just one last little bit to keep in mind is, we'll get back to that. Oh yes, and remember echo, there's a function called call echo, which is the thing that calls echo. And just to keep in mind, this red is the return address for call echo. And that's going to be important. So what we see then is the memory layout is our buff is normally big enough for 4 characters. There's sort of 20 bytes of unused or wasted space here. And then the actual return address, which is the return address for back to call echo, is stored on the stack. So when this program begins running, when echo starts to run, we'll find that this is the value on the stack for the return pointer. And if we type in a string of 23 characters, you'll see that it uses up this entire buffer. And remember, a string is terminated with a 0, 0. But it still hasn't. It's still within the region that was allocated on the stack for that. So it just barely fits into the stack. And that's why technically we overflowed the buffer, but we didn't really cause any harm because there was this extra space available. And so that's why I could type in that string of 23 characters and it worked fine. But now if I type in, this is an example showing actually 25 characters. So once I go beyond the 23 characters plus the null character, you'll see what I'm slowly starting to do is corrupt the byte representation of the return address. And so what happens, for example, here is that rather than trying to return back to where call echo where it was supposed to go back to, it goes back to some other part of your code that may or may not be a valid address, or might not have anything to do with the program you're trying to run. So this example shows it. And if I typed in the 24, let's see. Before I got it to run, this thing depends on what happens, how the code happens to get compiled. Oh yeah, so, okay. So actually you see here, this first string I typed is actually 24 characters long plus the null pointer. So, and we'll see why it should have crashed, because we actually wrote the low order byte of the return address. Here we typed in, this is 25 characters, and so that's the one I just showed where it really whacked the 2 bytes of the return address. So here we actually did overflow the buffer. And let's try and figure out why that didn't harm the program execution. I see a question?
So there was a segmentation fault in this case, but is it possible there could have been undefined behavior?
Yes, it could have been various other things could have. There's nothing, it hit a segmentation fault because it probably went to some weird part of the code and just started executing some random stuff and just got itself into trouble. But that's the point, is it's not predictable exactly what will happen when you do this. So this is the example of what actually happened the first time when I typed in a string that had 24 characters. And so this null byte at the end actually corrupted the return address. And so it was supposed to return back to this address 4006F6. And instead it will return back to the address 40600, which happens to be in some other weird function that's there. And it just sort of landed at some place here, and it's doing various things, but somehow it didn't really, didn't crash the program. And that's one of the frustrating things about this, is that things can go wrong in a program, and they don't always cause a crash. And so often a bug that's lurking there might be doing some weird stuff that you don't even know about. So that's all fine if it's just a way of crashing programs, and I mean, that's not great if it's controlling your pacemaker or something like that, but if it's just a homework assignment, it's like not a big deal. So, but what actually, and this is sort of only happened since attacking became a normal activity, which has only been the last 30 years, is that it gives an opportunity for a hacker or an attacker to inject code into the program and execute it. And that's what's called a code injection attack. And so the general scheme of it is I have this buffer that I can fill up with whatever bytes I want by feeding them to getS or whatever function is doing this copying. And what I can do then is set up and pass to it some bytes of actually that encode an executable, a little bit of executable code. You've seen in object dump, it's printing out these bytecode representations of instructions. So imagine you fed some of those bytes into your string. You encoded them in the string that you passed to getS. And then you might have to add some more sort of padding characters whose value doesn't matter, in order to then get a number back into the position where the return pointer is supposed to be. And so let's call that number B. It's going to be an address, one of these ones with, that represents a stack location. And that value B then is the starting address of the buffer, which happens to be where your exploit code, remember this is just executable instructions, were stored here. So now what will happen is when the program does its return here, it was supposed to return back to wherever it got called from, P. This is a typo. P calls Q, not bar. So it's supposed to return back to P, and the address, the return address, was stored here. But now I've overwritten that return address with this buffer position. So what will happen is the program counter will happily jump to this spot and start executing whatever it encounters, which are the instructions that you've inserted. And by that means, then, you can inject code into a machine, potentially somewhere else in the internet. If you could set up a scheme like this that would feed these bytes into that machine, and it would read it in with a function like getS, and then it would try to do its return, but it would start executing your code. So that's a classic code injection attack. And in fact, in this lab that you're going to start, it comes out at midnight, it's called the attack lab because you're going to do this yourself for part of the lab. And I think you'll find it pretty interesting. So this used to be a huge problem on programs. Yes?
On the last slide, so when you're trying to replace ret, how do you make sure that your new submitted ret overrides that exact line?
Well, that's part of the cleverness of being a hacker. You have to make sure it's in the right spot. But that's actually one of the easier parts, because, for example, if you have to know the binary code to be able to do this or be able to guess. So, for example, in that previous one, I could tell that it was allocating 24 bytes for that buffer. And so if I just made sure that the length of my exploit code plus the padding is 24 bytes, then right after that comes the return address. So that's actually pretty easy to do.
So there are ways to tell externally how much memory your program is accessing?
No, you have to have access. You have to. The reason why this works is it works if you have enough knowledge about the operating system that's running at the other end. For example, you know it's Linux. You know that you can look at what GCC tends to allocate for it. You somehow have access to information about the code itself that lets you do this. So anyways, this used to be a huge problem, and it started way back in 1988. The first internet attack was called the Morris worm, and at the time the internet was not a very big place, and it basically brought down a huge fraction of the machines that were on the internet at the time. Interestingly enough, CMU did not fall victim to this attack because we'd patched already the vulnerabilities that this particular program exploited. And that was the cause that the Software Engineering Institute runs an organization called CERT, the Computer Emergency Response Team. And that team was set up in response to this attack, the Morris worm attack. We'll also see an interesting example between two companies in messaging services and many others. It's been the sort of standard attack mechanism for many years. And fortunately nowadays there's a few things that make the attacking less likely to be successful, and so it's not as huge a problem as it used to be. But still it's a source of many vulnerabilities in programs. So let's see, I won't talk too much about this, but it used to be in the original implementation of, there's a command that most systems have now disabled, that you could request information about somebody in some remote location. It would send a message to that location, and then it would reply back. And it used getS. The actual original implementation called getS to read the input string that was being sent to it. And then there was an interesting one. You guys don't remember messaging, instant messaging, but before, it used to be that people would talk to each other on their computers by sending messages, sort of like you send text messages today. But there's an interesting thing that there was a company, still exists, but it's a shadow of its former self, called AOL, which ran the most popular internet services and it had the most popular instant messaging program. And Microsoft came out with its own client, its own program that you could run on your machine and communicate to other people on this messaging system. So the Microsoft code was running on your machine, but it would use the servers that were being run by AOL to manage this messaging traffic. And the funny story was this Microsoft program would work fine. You could communicate with your friends who had different messaging clients, and it all seemed compatible. But then suddenly the people that were running the Microsoft version of the software, it wouldn't work. And then Microsoft people figured out how to patch it, and then it would work for a while, and then it wouldn't work. And what was happening was AOL was using a bug in its own code to be able to determine who's basically peek into the machines on the client side and do a buffer overflow attack on your code that you're running on your machine, and then basically peek around and see, does this look like AOL code, or is it some foreign code? And so it was basically able to use its own security weakness to figure out this information. And that got disclosed by a sort of funny message from somebody who called himself Phil Bucking. And it was determined that this email originated from somewhere within Microsoft. So anyways, and you can read more about it in the book or on the slide. So, fun stories. So in general, in the security world, you're supposed to distinguish between the idea of a worm and a virus, although people aren't very good at doing that. So a worm is a program that can run on its own and propagate itself from one place to the other and replicate it. A virus is like a biological virus. It doesn't live on its own. It works by attacking a program and basically modifying that program's behavior. So that gives you the basic idea of buffer overflows, and you'll see it more firsthand. So let's look at techniques that machines can use to make themselves less vulnerable to these attacks. Well, first of all, you, the application or the writer on the server side, can write code that's more secure. So for example, what you're supposed to do instead of getS is use a function called fgetS. And fgetS has a property that it passes a parameter, which is the maximum number of bytes that the program should read. And if there's more bytes than that in the input, it will just truncate the input. So you're really supposed to use fgetS and give a limit. Similarly, strcpy, there's a version of it called stern_copy where you can give a limit. And with scanf, you're supposed to be careful about using the %s. And there's even a terminology you can say % give a number that's the maximum length of the string it should read. So there's various places you can protect your code to make sure it won't overflow buffers. Unfortunately, and a lot of code has been, you'd call it hardening. It's been, people have gone through it, and it's a lot of work because there's a lot of places in programs where you're copying strings from one place to another. And there are a lot of real subtleties, like when you're converting from Unicode to bytes and so forth, that you're going back and forth between different character encodings. But for the large part, and there's tools that the code developers have created to help track down these bugs. So it's become a little bit safer out there, but there's still vulnerabilities. So then there's other parts where you just try to build in safeguards into the system that would make it much harder to do a buffer overflow exploit like I showed you. And so one of them is called stack randomization, or it goes by a more general term that's abbreviated ASLR, which stands for Address Space Layout Randomization. And the idea of it is to make it so every time a program runs, the addresses change a little bit or a lot, so that you can't reliably know where things are going to be in the code. So imagine, for example, and the way it's implemented is before, in the sort of run-up of your program when it first starts up, but before your main routine gets called, it will just do an allocation on the stack of some random number of bytes of storage, a fair amount, like maybe a megabyte roughly of storage where the exact number is randomly chosen. And what that means is that the address of the stack of all the different positions of all the local storage on the stack will shift up and down from one run to another. And we can actually see that in this example I showed. So I have a program here. It's not a very interesting program, I'll show you, except to demonstrate these ideas. All it's doing is there's some it's based on that one I already showed called locate, but this one, there's a global variable, there's some functions, there's something that gets allocated by malloc, and there's something that is a local variable stored on the stack. And so what I'll do is show addresses that are chosen. The address of this variable then will be a stack address, a local variable. Global will be this one that gets allocated globally. The heap is something allocated with malloc. And then this function useless will count as a code address. And now when I run it, you'll see from one run to another that if some of these stay the same and some of them change. So in particular, the global variable is the same, 60102C. And the code is the same, 400590 is the same every execution. But you'll see this local variable, it's a stack address, but you see that the lower half dozen or so bytes are actually changing from one run to another. 1, 2, 3, 4, 5. So 5 bytes, so that's, or 5 hex digits, I'm sorry. So that's 2 to the 20th. So roughly a megabyte of variation is going on in stack addresses there. And similarly, you'll see that the heap addresses are also varying from one to another, from one execution to the other. So malloc has built into it some amount of randomness too in its allocation. So why is that? What's the purpose of that? Well, as I told you, this code injection vulnerability relies on the fact that you can load up this buffer with some executable code, but somehow you have to know how to get to the start of that code. And so this is the attack is relying on the fact that it can somehow predict what this address of the buffer is, and so that it can store it in the right part of the string, encode it in the right part of the string so it will show up where the return pointer is supposed to be, and have it jump to that location. But now with this randomization, this number is varying by quite a bit, sort of million over a range of 1 million or so values. So there's no way in advance, even if I have an exact copy of the code and I even had access to the system itself and could run it, I can't predict from one run to the next where it's going to be. So that gives, it sort of thwarts this particular attack to make it using this randomization. Another idea that's fairly straightforward, but it took a long time for the hardware people to implement this, is, well, why is there supposed to be code on the stack in the first place? Isn't the code supposed to be located down in the text segment where it can be sort of specially identified as being executable? So in the original x86, there's a 1-bit flag for each region of memory saying, is it actually 2 1-bit flags. One is, can this be written to? So that you can prevent overwrites of things like string constants. And then the other is, can I read it? And read means access those bytes. And it was interpreted that readable and executable were the same thing. I can read it, I can execute it. And that was the rules. In a sort of last 10 years or so, starting first with AMD and then Intel, have added a 3rd bit that says, is this executable or not? Similarly to the permissions you have on a file in Unix. Is it readable, writable, executable? Those are 3 separate permission bits that are allowed. So by simply marking the stack as not executable, it'll also thwart this particular attack because I have to be able to execute these bytes that I've injected into the system. And then there's a final idea, which is actually fairly effective too, which they call a canary that they build into the stack. And some of you actually encountered this code already in looking at your bombs because we've been getting some questions about it. So let me just give you an example here. And this one's called buffdemo-sp because it's been compiled with what they call a stack protector. And this one, now, it's the same code as before. It's just compiled a little bit differently. What you'll find is I can give a string of length 8 and not have a problem. But if I now have 9 characters, it will dump out with this very strange exit error message that is an indication that it's detected a attempt to smash the stack. So buffer overflow is sometimes called stack smashing. So it detected somehow that even though my code was still the same old crappy code from before of a very small buffer allocation and no protection, somehow the system protected me from myself. And that's by a relatively simple trick that's fairly clever, though. What they call a stack canary. So the term canary comes back from back in the coal mining days of old, before they had very good ways of measuring things. They'd take a bird down with them in a cage. And a canary has a property that it's very susceptible to dying if there's methane gas present. So these miners would be down there working and they'd see their bird keel over and say, oh, we got a problem here, let's get out fast. So that's why they call it a canary in a coal mine sometimes. Some kind of warning signal that something's not right here. And in general with GCC, if you invoke it with a stack protector, nowadays that's the default. So even without you saying anything, this code will get built into it. And so let's look at what that canary code looks like and how it does its thing. It's really pretty clever, as I said. And some of you have already observed this strange kind of memory reference in a register reference in the code in your bomb labs, because it was compiled with the stack protecting enabled, because that's the default. And so in particular, what this code shows is it's allocating, as before, 24 bytes on the stack, But now it's getting some number, and we'll talk in a second what that means, and storing it at position 8, offset from the stack pointer. And then the rest of the code, and then it zeroes that out. That's not too worried. And then it looks like your previous code, that it's passing a pointer to the stack, the top of the stack, as the argument to getS. And getS gets called, and then putS gets called. But now there's some more code here that involves this strange-looking register. And then there's some kind of test, and then if that test fails, it will call this code that you just saw printed out, this error message. So let's see what that all means. What that means is that at offset 8 from the stack pointer, it's putting in 8 bytes of value that it's retrieving from a special register. So FS is a reference to a type of register that was created for the original 8086 and is now completely obsolete, but it's still there for backward compatibility mode. But what it is, and I've looked and I've never fully been able to find the documentation on it. It's able to read from a part of memory, a set of values that you can't otherwise get to. And so that's the canary. It's getting, somehow it's grabbing 8 bytes from somewhere, storing it as this canary value. And then if you give like a 7-character input, so you would affect the canary. And so what happens when it returns from the 2 calls from getS and putS, before it exits, what it's trying to detect is, has this buffer somehow overflowed and potentially at risk of corrupting some other part of the stack? So basically what it does is it retrieves back from the stack what is the current value of this canary. And it's comparing it to what it should be by retrieving that back from this special region. And if they're equal, it says fine. But if they're not equal, it's detecting that it's got corrupted. So just like the canary in the coal mine, if these bytes get corrupted in any form, it's an indication that something went wrong. Now, that example shows that if I have a 7-character string, then I'm not going to corrupt the canary. But you notice I just got away with an 8-character string. So let me just see what's going on here. Wait. I want an 8-character string, right? Oh, wait. Sorry, I have to look. I don't have the code in front of me, so I have to look at it. So anyways, here's where it's subtracting 24 from the stack pointer. And then the next instruction is retrieving this canary value. So let's figure out what the canary is. Right now we are at 7.2f. So we're at the first instruction here. Let's do another step. So this is the canary. And it's, you'll see actually when from one run to another you get a different value of it. So it's purposely put in there in a way that it's unpredictable. The one thing you'll notice is that the low order byte is at zeros. And so apparently they knew that it's so common to have sort of off by one bugs with strings where you don't allocate enough space for the null terminator that they said, well, rather than having a canary that will detect that byte being corrupted, we'll just sort of give that byte away. And so that's why it's letting me type in 8 characters, and it's overriding this low order byte of the canary later on, but that's not going to affect anything. But let's give it 9 characters, 10 character string, a 9 character string. Well, I'm not finding it where I thought it would be. Anyways, this will corrupt the stack. But what I was showing you, the main idea is the canary is some value that gets pulled out, and it will vary from one time to the next. And it's letting you get away with 8 characters plus the null terminator, but anything more, and it will detect that corruption. Okay, so now we've seen 3 different protections. Well, 4. One is write better code. But there's 3 protections that are done by the system that have nothing to do with your code. Right? One is to randomize the stack position so it's harder to figure out where the start addresses are. The second is to make the stack so it's not executable, so you can't put code on that. And then the third is to use a stack canary or other mechanisms to detect a potential buffer overflow at the source. So now there's another attack that was developed in response to some of these that is still often successful. It's called return-oriented programming. And for your attack lab, you're going to be doing these attacks too. That's why the attack lab is different than the old lab. The old lab just did code injection exploits. Now you're doing both code injection and return-oriented programming. So the idea of this is if you were a hacker, you're frustrated because of these 3 techniques: stack randomization, non-executable stack, and canaries. Well, I can't fix the canary problem. That actually, the canary is a pretty secure technique. I've never seen anyone able to bypass a stack canary. But the other 2, you can do it using this technique. And the strategy is, so we don't know where the stack is, but we could still, but we know where the code is, because you saw in that example, the code, my layout randomization was shifting the stack positions and the heap positions, but it wasn't changing either global variables or the code itself. So what if I can find some code that's sort of already there in the existing part of the program and use that instead of my own code that I've injected. And of course, in general, you're not going to find exactly lying there the exact program you want to execute that will cause whatever harm you intend to do, because that's not usually compiled into most programs. But if I could sort of string together little segments of code and somehow put together a series of little sequences of code, maybe I can get something useful done. And so that's the idea of this return-oriented programming. And the idea of it is to find what are known as gadgets. And a gadget is a sequence of bytes that are, represent part of the executable program, where the last byte, this is x86 talking here, has a hex value C3, which is how the ret instruction, the return instruction, is encoded in x86, both IA32 and x86-64. And so as an example, the easy case is where there's some function and it implements some operation that I might find useful as an attacker to be able to do. So for example, this function is computing a times b plus c. And if I look at just the last two instructions from there, one of them is a LEA, which is performing addition, and the other is doing a return. So I can think of this little 5-byte chunk as a way, if I could get some data in registers RDI and RDX, then I could compute their sum and stick it in RAX. So imagine taking your program you're trying to execute and breaking it up into these little fragments, and you want to somehow find a little block of code somewhere to implement each of these fragments. And then the interesting part is, because they each end in C3, this return, it has this, well, let me get to that in a minute. So that's sort of the obvious way that you pull out, this is an addition, which you'd expect because that was in the original C code. But here's an example of a gadget that has nothing to do with the original C code. It just happens to match the byte pattern of some existing code. So this function seems to not do anything too terribly useful from a hacker's point of view. But if you look at this particular byte sequence, that happens to encode the instruction move Q RAX to RDI. And C3 encodes ret. So, and you can see if this is at address 4D9, that's 4DA, 4DB, 4DC. So at address 400-4DC, if you could start executing here, it would first do a move, and then it would do a return. So I'm sort of taking advantage of the fact in x86 it's this byte-oriented instruction sequence. And if I sort of go off the aligned instructions, I can often find useful things to do. So that's what's called a gadget. And you might ask, well, what's so special about having them end in a return? Well, imagine I could fill up my buffer, instead of with executable code, I could fill it up with a series of gadget addresses. So each gadget then is some series of bytes where the final byte is C3. And I'll actually position this, I'll position this at some place where you're actually going to do the initial return instruction from before. So if I can somehow get the program to return, execute a ret right now, what it will do is return will pick an address off of the stack, pop an address, and begin executing. So that will start this code executing, and it will hit the C3, the ret instruction at the end, which will, again, take an address, pop it off the stack, and begin executing. So it will start executing the second gadget. And so you'll see what will happen is we're effectively concatenating these pieces of code together where it's using a ret to get from the end of one gadget to the start of the next. And so that's why it's called return-oriented programming. It's a way to, instead of sequencing programs using a program counter like you normally do, you're sequencing programs using the sort of peculiar behavior of this particular x86, how returns work in that program. And remember, there's enough x86 out there that if I can find a way to attack them, I'm in a pretty good place. It's also possible to attack other processors this way too. It's just particularly nice on x86. So that's the idea of return-oriented programming, and you'll do this yourself. You'll find gadgets, string them together to do different things in the attack lab. But I'll point out that this still doesn't. So this stack canary idea is still successful at detecting buffer overflows fairly effectively. So in your attack lab, for example, we've carefully compiled the code to make it vulnerable to these attacks. Otherwise, it would be a lot harder lab. Like if you could do this, you could probably go into the dark world and be very successful. So we're actually sort of exposing the vulnerability, but in the first part of the lab, you're using code injection attacks. So we've had to disable stack randomization and also make the stack executable. So we had to sort of, but in the return-oriented programming, we re-enable that so that the stack is not executable. It keeps jumping around randomly, but we've turned off the stack canary. So you'll be able to overflow the buffer and put in your gadget addresses and build up attacks that way. So I think you'll find by actually doing it, you learn a lot more than you can by just hearing about it. Oh, you might ask, why do we teach you this stuff, right? Aren't we supposed to teach you to be good and not evil? Well, there's a couple reasons. One is you're going to learn a lot about machine program execution and how stacks work and how byte instructions are encoded and stuff like that. You'll use the tools, GDB, object dump, and all those even more than you did with the bomb lab. So you'll learn a lot. The other is we assume that you will work for forces of good, but to be a good person, you also have to know what the bad people do. So part of it is to become more effective as a force for good. Okay, so the final thing to talk about today is unions. And the observation about a union in C is the declaration of it looks a lot like a struct, where there's these different fields and they're named and they can have different types and there can be pointers to unions and all that stuff. But they're actually totally different what they do. You recall with a struct what happens is it allocates enough memory for all the fields to coexist and potentially adding padding bytes for what a union does is it only allocates enough storage for the maximum field in it. And it assumes that you're only going to be using one of the possible fields. And it will literally store on top of these fields get stored on top of each other, so that if you try to use multiple fields, you can mess things up. And it's not for that purpose of doing multiple values. It's for the purpose of, for example, if I know I'm only going to use one of these, or it's also a way to create essentially an alias that will let you reference memory in different ways. So for example, in your data lab, you were manipulating the bit level representations of floating point numbers. And in our code that would then convert that to an actual float, we used a union where the union is either to view this field of 4 bytes as an unsigned or as a float. And so I can convert from an unsigned to its float representation by just storing the unsigned value in this union and retrieving it as if it were float. And this is a fundamentally different operation than casting, because you recall when you take an unsigned value and you cast it to a float, you actually change the bits. You change it into the floating point number that's the closest match to this particular a number. It would be the equivalent of the function you implemented, float underscore u2f. But this one actually doesn't change bits. It just changes, the numeric value changes quite a bit. So it's a useful technique to do that, to be able to override the type system and get to bit representations. And this actually turns out to be one of the places, too, where byte ordering will show up in programs if you're not careful. So in particular, with this union, I can view a block of 8 bytes as either 8 characters, 4 shorts, 2 ints, or 1 long. And on a 64-bit machine, like is shown here, where long is 64 bits, you'll see that you're able to look at things as either as the individual bytes making it up, or some longer aggregation of those bytes. And you'll actually find that depending on what machine you run it on, you'll get different results because of the byte ordering of the different machines. So this goes through it, what happens when you run on different machines. But you'll notice in particular that on an i32 machine, a 32-bit machine, it's coming off in this byte pattern, F3, F2, F1, F0. And on a Sun, back when they existed, you'd get the opposite because of the byte ordering. And now on an x86-64, where a long is 64 bits, you get 8 bytes. And you can also determine from this, if you look carefully, that it's in it's a little Indian order, because this is the least significant byte is F0, which is the first byte, F0. So it's also a way to get to the low-level bytes, but when you use this kind of thing, you're sort of intentionally telling the C compiler, trust me, I know what I'm doing, you don't have to protect me from myself. And so if you're not careful, you can write code where, because of a byte ordering problem or something like that, it won't run properly on some machines. So just to summarize then, we've looked then at the 3 compound types in C, the ways you can aggregate smaller types into larger ones. You can make an array of identical elements indexed by a number, the position, and that usually turns into some kind of scaled computation to get to the particular place. We've seen structures where it's a fixed number of fields, but the fields can be of different type and they're referenced by their names. And that usually turns into some type of displacement off of the original position. And then a union is just a way of sort of piling up in one place a number of different fields. And so all it does is allocate the maximum number of bytes for that and doesn't create enough space for them all to be there at the same time. Okay, that's it for today then.